Right. So as I was, I said at the beginning of the office hours, but my plan is today I will just do some examples, mention some final things. Although already like kind of all the theory that I wanted to discuss, we already discussed. And then on Monday, I figured that since you would have had the weekend to study, then we can just go over problems that either you have questions about, or you're getting stuck with, or we can, go over any other things that you want. I will send you some more extra practice problems tomorrow. Like kind of like this usual practice exam problems that I have been sending you before. So yeah, and check also the study guide because again, like I'll be giving you some formulas on the exam, so you can check on the study guide the formulas I'll be giving you, and then like that way you don't have to memorize them, but at least you should still know how to recognize them. And I was going like if you read the details on the study guide, it will still be 2 parts, the exam, but each part is now 80 minutes, so it's twice as long each part. But I'll probably be going for like 4 or 5 problems on each part. I still have to write the problem. So, you should have more time than on the midterms because it's twice the amount of time, but I'm not doubling the number of problems. So I would go, I think I'll just go with 4 or 5. I guess in theory, it is cumulative, but the thing is like there's a lot of repetition and overlap on the problems. Definitely like at least 5 would be, or like at a minimum 5 of the problems would be on new stuff, like involving continuous probabilities or joint distributions, things of that sort. And then there might be 2 or 3, which are like this Bayes theorem, conditional expectation, things from like you may have seen on the earlier midterms, on the first 2 midterms, but like the bias will be more on the new material because that still is a lot of material which we haven't like tested on an exam. Like there was a lot of those 4 chapters in the book are like a lot of stuff. So like I didn't cover. There are many if you have been reading the book, there are things that I'm ignoring, but otherwise we wouldn't have had like a lot of time. But yeah, so for today, like what I was going more for was just to do some examples, and then on Monday, if that sounds good, then we can just go over the examples that you wanted to ask me about that you're having troubles with. So yeah, let me start with one of actually on the guide, because I don't think I have emphasized this enough, and it would be a good idea to emphasize it today.
Professor?
Yes. You can
I have a question about quiz. Do we have quiz today, Eman?
No, it was just I think did I give you like an assignment, or I never gave you the other assignment. Let me check actually. No, let's see. No, it would be right. So they're still on. Oh, but that was already due on 8th, right? So I never gave you anything new. So yeah, so I guess there were no more new assignments or anything. So yeah, like if there was a quiz on the syllabus today, I'll just give you the points or whatever. Yeah, but so yeah, no quiz today, and no quiz on Monday. I don't know if we were supposed to have one on the according to the syllabus, but yeah, there wouldn't be a quiz today or on Monday. That sounds good. Yeah, I don't know, like, right. I think there was like a quiz 11 and 12 on the syllabus, right? Officially, but I'll just give you those points. Like, I guess I can. Let me start with okay. Yeah, let me start doing like this problem 74 on the PDF, because I think it's kind of useful to just clarify something. I'll write it because I don't expect to post like a new version of the PDF, but depending, on which versions you have had, then you have been checking, like keeping track of the numbers may be confusing. So let me write the statement of the problem here. So it says the annual rainfall random variable with mean 40.2 inches and standard deviation 8.4 inches. So there are two questions here. So what is the probability that the next year's rainfall will exceed 44 inches?
What is the distribution of this random variable? Is it
Oh, that's actually what I was going to make the comment about. Yeah. So
okay.
that's the thing. The philosophy is like if you know if you only know the expectation and the random and the standard deviation of the random variable, you should assume that it's a normal distribution. That's because that's just like the one that the normal distribution is the one that maximizes the entropy. So it's kind of like a version of this maximum entropy principle. So yeah, but that's actually why I wanted to choose this problem to write that down explicitly, because I may have mentioned that very briefly at some point that the Gaussian maximizes the entropy, but it's kind of like the rule of thumb to just assume that it's a Gaussian. So I'll write that down explicitly. So next year's rainfall will exceed 44 inches. And the yearly rainfalls in exactly 3 of the next 7 years. $44 each. Okay, so right. Let me give you a chance to copy this one, and then I'll write that down. The stuff that I was mentioning a couple of moments ago. So okay, so right, as you can see, like the only thing that they're telling you about the random variable, which is being represented by the annual rainfall. So we have this x random variable, which is the annual rainfall. The only thing we know about this random variable is the expected value and the variance, right? So I mean, you can think. I mean, there are many ways to think about it, but like one way to think about one reason to think about this is because of this maximum entropy principle. When you only know E of x and the variance, we will assume that x has a normal distribution of has a normal distribution or has like a Gaussian distribution. We will assume that x has normal, Gaussian distribution of that mean and variance. Okay, so that's kind of like our working philosophy. So if I don't say if I don't say anything about the variance, then if I don't say anything about the random variable except the mean and the variance, then you should assume that it's just normal. Okay. Again, you can think about it as coming from like this maximum entropy principle. If you like that stuff. Now, here's another important thing to keep an eye on. Okay. So let's see, like just as a notational thing. Like the usual convention is that Z is like, if you were talking about Gaussians, in the world of Gaussians, Z is referred to it's like the letter that's reserved for the Gaussian with mean 0 and standard deviation 1. Okay, this is like the one that literally looks like this bell curve or this Gaussian curve center at the origin with standard deviation 1. But then the important thing about this Gaussian is that any other random variable can be written in terms of any other Gaussian random variable can be written in terms of Z. Okay, any other Gaussian random variable can be expressed as a dilation, as a rescaling and a shift of Z. Any other Gaussian random variable can be expressed as a shift / dilation How was that done? Well, basically, you can write x as sigma z plus mu. Okay, and let's just check that that works, that it has a correct properties, because what would be the expected value of x? Well, the expected value of x would just be sigma times the expected value of z plus mu. Like the reason why is that, remember, the expected value is kind of linear. So computing the expected value of this is just like the expected value of this plus the expected value of this. But mu is like a constant and sigma is a constant. So you can take out the sigma. It's kind of like that. I mean, the expected value is like an integral, right? So it's kind of like basically the same properties of the integral, the linearity of the integral. But then the standard one has mean 0. So the expected value of this translation is just mu. And then what would be the variance of x? The variance of x would be the variance of this dilation shift. But if you remember, like the formula for the variance, how it behaves on the rescalings, is you just square the number in front of the random variable times the variance of the original random variable. But the thing is like this one has variance 1, so that means that the variance of x is sigma squared. So that means that if you start from the standard normal distribution of mean 0 and standard deviation 1 and do this rescaling trick, that actually is generating for you all the other all the other Gaussians. So that's kind of useful because in practice, if you open like a book on probability or a book on statistics, they will have like an appendix where like you can see like, you know, the Gaussian curve with a bunch of values for the probabilities. And you can't they obviously only give those values for like the standard one. But the idea is that once you have the values for the standard one, every other Gaussian is connected to the standard one. So you can always like kind of you can always extract the values that you care about by doing this rescaling property. So actually, I'll show you how that looks in this example. But I wanted to mention this first because I don't think I emphasized that enough. So yeah, like the philosophy is mean and standard deviation known, assume that it's a Gaussian, basically. Okay, and so how can we do part A? Well, are there any questions about this before I continue? Is that making sense so far, so good? So what is the question in part A? The question in part A is that the probability that the rainfall will exceed 44 inches, right? So you're asking for the probability that X will be greater or equal to 44. But that's where you have to use the fact that you can write X in terms of the actual standard normal distribution. So this is like the probability that sigma Z plus mu is less or equal to 44. But we know that the mu, what was the standard deviation in this problem was 8.4. And what was mu in this problem? It was 40.2. So you get something like this. Right, so this is really the probability. I mean, and oops, like I should put this. I think I somehow, this, like I have to make sure that my twos do not look like the letter Z. So, and this is like a kind of inside, there's like a probability outside of this, but when you can solve for this inequality in the usual way, so this would be like, 44 minus 40.2 over 8.4. Right, so that's how you would solve the inequality for Z. So this is just asking for the probability that Z is greater or equal to 0.32. Oh, sorry. What is that? 0.4524. I had done it before. So. Okay, and then at this point, like the question is, I mean, like again, like I suppose, like, like if it were like okay, so I would you can leave the answer like that because like not like it's not there's like of course like I'll give you what the answer is, but it's like the only reason I know the answer is because like you plug it in either Wolfram Alpha or like this table to find the values. But once you reach the probability in terms of like the standard distribution, like the normal one, like of mean zero and standard deviation one, that like I mean that is secret. Like the answer is already there. It's just like a number that we cannot compute because it would be doing like the improper integral. I mean, this is literally like this corresponds to what? It would correspond to the integral from 0.4524 to infinity of 1 over root of 2 pi e to the minus c squared over 2 dz, which I don't know what that is, but again, if you check like the tables of values, that is 0.3253. But so what I'm saying is that you can leave the answer like this if you want, because I don't think it's worth like giving you that table on the exam. It's like just a bunch of numbers, and it's kind of like there's not too much in like just looking the value of the table. So like, but it's like what is important is to understand that X, like the two things that are important in this problem is just to understand that any Gaussian can be written in terms of the standard one that's valuable, and also understanding that like if you only know the mean and the variance, then you should assume that it's normal. So those are kind of the two key ideas that you need in this problem. But yeah, you can just leave the answer. You can just leave the answer in terms of the probability for C.
Can this problem be solved in polar coordinates?
Well, that's the thing. Like it is. You don't gain too much by doing the polar coordinate trick. The polar coordinate, like you mean, like how would you actually find this integral?
Yeah.
You don't gain too much doing that. The polar coordinate trick is useful when like the integral goes from minus infinity. When it went from minus infinity to infinity, like both bounds are infinite. Then that is useful because then the double if you remember how we did it in polar, then you did know like the bounds of integration. Like the bounds of integration in polar become nice, but here it actually doesn't help you too much to do that. Like the way in which this, like the reason why I can put 0.3253 here is that like there are numerical methods for approximating integrals, like independent of whether they're Gaussians or not, and that's what is being done here to evaluate this. So it's not so much about like the polar coordinate stuff. For this particular value, for the one that was from minus infinity to infinity, yeah, the polar coordinate is actually useful. But you wouldn't, if you try it, you'll see that you wouldn't gain too much in this case, because the lower bound is not very useful for.
I tried it. I just switched the integral. You could write the probability as 1 minus c is less than or equal to 0.4. And then your bounds is just 0 to a, so you have like a square.
Well, right, but the thing is, like, if you switch to polar, right, then you have to rewrite the. I mean,
and r is just a times secant theta, where a is 0.4.
Well, right. Let's see. So, right, like you could say this is like 1. Okay, let me just write this first. You can leave this in terms of C, in terms of C, and okay. But yeah, if you want to write this like 1 minus the probability that Z is less than 0.4524, you're saying?
Yeah.
And then right, like I mean there okay, but then like the question is okay, so this is like you're trying to do like a double integral in polar coordinates, right? That's what you're saying. Right, so this would become I mean it depends on like how you want to switch it. I mean, because this is like a do you want to do like the integral first in polar and then take the square root of that to find the value, or like what were you thinking specifically?
Yeah, because the bounds here is just 0 to a, right? For both, where a is 0.4.
Okay, right. Okay, I see what you're trying to do. So right, like you could say we
so
could
your
start
region
with something
of integration is a square.
Right. Yes. Okay. Right. So I agree with that. Right. You could let's call these just junk. Well, it's not. It's not. The thing is, like the Gaussian can take. The Gaussian can take actually negative values. So the bounds go from minus infinity to a. They don't go from 0. Oh, okay. I
You
guess
can't
in
have
this
negative
case,
rainfall, right?
Right. Yeah. Okay. I would. Yes, that is a point well taken. So because if you want to use the assumption that rain cannot like high for the rain is always a negative, then like I would say you can do that. That would be justified. That's fine. Yes, that's like a reasonable a fact to use. Okay, then you want to say I want to put the values for this square in polar coordinates, right? And then you would have to break. I mean, when you put the bounds in polar coordinates, you do have to break the integral here, right? Like it cannot be written just with a single double integral in polar, right?
You can multiply it by 2 since it's a square, and just have theta go from 0 to pi over, or yeah, 0 to pi over.
Well, it depends. Like if you have here a and you have here a, you have to check that the integral like is symmetric. like, let's see, can you like you would have like here something like, okay, you would have something like this. Yeah, you're trying to write this here. But then is that I mean, you can multiply by 2 if the integral is symmetric, right? With respect to the line. But is the integrand symmetric with respect? I mean, it doesn't matter. It's not that it would be too much of a extra trouble to, you know, to break it into 2 pieces. Like if one of the pieces can be integrated, then you could integrate the other piece easily. So yeah, we could just focus on the first one, which is the integral from 0 to pi over 4. And then the theorem from, you know, what is the radius? Like, as you're saying, like this would be x equals a. So it would be like secant, right, of theta, or secant, a, what, like this is a equals r cosine of theta. So it would be a times secant of theta, right?
Yeah.
And then the question is, okay, so I agree that the first one would be easy to integrate, right, with respect to r, because that's just like what, like, I mean, let's ignore the constants, like it's like minus e to the r squared, right? Like that's the integrand, right? But you have to evaluate this at 0 and it's a secant of theta, right? Is that making sense?
Yeah, that'd be difficult.
You don't know, you don't want to do that, trust me. So is that okay? Yeah, it's not too convenient. You see, I mean, it's actually useful to try this to see what would happen. But even if you, you know, because in the end after a constant, it's just like you're doing like, I mean, obviously I'm dropping some constants here, but like the integrand, like the factor in the integrand is minus a squared secant square of theta. And I don't know who knows how to integrate that. I certainly did not. So you see, like it does, you can do something about it. You can do less than you may have thought. So the polar coordinate trick, which is really useful, is actually really sensitive on having the bounds from minus infinity to infinity, 0, infinity, and you know, otherwise, otherwise this angle is you know, a complete mess. You do benefit from it, like the theta bounds to, you know, it really you need like the bound for r to go from 0 to infinity for that to work. Otherwise, you don't really have a good way to integrate it. But I mean, yeah, but I'm glad we did this because it's like a natural thing to try. So, but it is like a mess. So, yeah. So what I'm saying is that, you know, for this problem, I don't see too much of a point in, you know, let me just write this as an aside. I'll keep it here. So this is an aside. I don't like, you know, this is what I find valuable. And then after that, like it's just like going either, you know, to a numerical table of integration. And that's fine, but it's because it's useful to have like a sense of what the actual probability, like the number is, but it's not like a, you know, it's not like really too much of a skill. So yeah, so if you just leave the answer like on the exam in terms of z, that's okay with me. But do leave it in terms of z, because just like writing x is greater or equal to 40, that doesn't really not say too much, right? But like in understanding that you can reference like the standard distribution, that is useful. So that is like the valuable thing here. Is that making sense? Any other questions up to this point? And then the second part was part B, that the in the next 7 years, exactly 3 of them the rain will be more than 44 inches, right? So it's now that in the next 7 years, on three of them, the rain will be will exceed 44 inches, right? And then, I mean, this is like a good example where like, stuff from the first midterm combines with like the recent stuff, because you can call like, you can call A the event that, the rain on a given year exceeds 44. And so part A gave you the probability for A, right? Like part A is actually computed that probability, right? P of A was like the probability that C was like more less or equal. I mean, whether there's greater or equal or strict inequality, that doesn't change too much because it represents. So you don't have to worry too much about whether you choose like greater or equal or strictly greater. That doesn't affect these integrals. So that's fine. Okay, and
So is this just
so
a binomial?
it is like exactly that's the point, right? It is like a binomial because you only need like if you consider a success the range exceeding 44, right? It is exactly the binomial distribution. So it's a binomial where what we're counting as success is like range being above 44. So we can call this even P, right? To just remind you of the notation for the binomial distribution, range bigger more than 44. So yeah, the probability of 3 successes, right, in the binomial distribution. Oh, it just 7 chooses 3, right? Because of the 7 years, you have to put 3 successes somewhere. Like it's like putting 3 ones. The 7 years choosing 3 places to put like a 1 for representing success, and then P to the 3, and then Q to the 4, right? So, and you see, like, this is like a question that naturally combines like the new stuff with the older stuff. So that's kind of like more along the lines of what I'm interested in. Like, it's like so that's why it's kind of difficult to, separate the new material from the old material, because like somehow like along the calculations, like the older stuff comes in. And Q was like here 1 minus P, right? As usual. Is that making sense? So that is how this problem would be solved. Okay, are there any questions about this? Let me see. Let me see. Okay, and then there was also another interesting problem that I was asked about during office hours, which is this problem 92 on the PDF. I'll also write it. I'll just do 92B because I realized the 90, like what I was in office hours, I realized that 92A required some things about conditional expectation that I don't think I went over. So we can you can ignore part A of that problem. So let me just do 92B. Part A. So what 92B says is like you have 2 types of batteries. You have 2 types of batteries. Okay. You have type A batteries. You have type A, which have last for an amount of time of the amount of time they last. Has a mean of 50 minutes. I guess this, like, I don't think I wrote the units, but it should be 50 minutes. Or I guess, well, for batteries, it's more reasonable maybe to think that days or hours would be, let's say hours. A battery that only lasted 50 minutes would be like too profitable, right? So standard deviation, 15 hours. And type B batteries last for type B batteries, the amount of time they last has a mean of what's here, 30 hours and standard deviation of 6 hours. Exactly. Well, I mean, right. You can, like, in your head, you could choose your favorite justification. You either, I suppose, for the problem that is asking here, which was about the total sum, you could go with either explanation, but you know, I am more sympathetic to the maximum entropy principle explanation. And so I would just think about it for that reason, but you can, like, yeah, you could think of either one of them as being okay justifications. But like if you open like a biology or statistics books or many books like where probability methods are used, many times they just invoke the central limit theorem to justify Gaussian distributions. I find it more like elegant just to think about this maximum entropy principle, but it's more like of a preference. But yeah, like, so either is fine in this context for what it's going to ask. I mean, obviously this was not the right course to get into those things, but there's always like a lot of like, different schools of thought about how to think about probability theory and things like that. So yeah, there's still some controversies on the foundations like of probability theory, but like, for practical purposes, like sometimes those controversies do not create too much of a difference, but yeah, there's still some variations about, how to think about probability and things of that sort. So depending on your preferences, like you may have like different reasons for, like, for example, assuming that the distribution is normal, but more or less everyone would end up agreeing that you should just assume that it's normal, but that you would just come at it from different angles. So the question what it was asking is like, if there are 20 batteries of type A and 20 of type B, find that if there are and in a second, I'll also give you like a nice application of well, the law of large numbers, you could think. And yeah, after I do this one, I'll give you a cool application about the law of large numbers. what is the probability the total life of the 40 batteries exceeds 1700 hours? What is the probability? That the total life of all 40 batteries exceed 1700 hours. Okay, so yeah, as we were saying, like since we know only the mean and the variance, you can assume that they're random variables. So type A would be like a random variable, a normal distribution or a Gaussian. But what is this Gaussian? Again, like the cool thing is that you can write all the Gaussians in terms of the truly standard one. So because the mean is 51 and the standard deviation, sorry, because the mean is 50 hours and the standard deviation is 15, you can write it as 15 z plus 50. And the type B batteries are Gaussians also. No, but this ones take the form of z6z plus 30. Okay, so again, like it is very useful in practice to think of them as all referring to the same, and it's always useful to know that you can write them in terms of the standard ones. But we have 20 of type A, so you can call them x1, xa1, xa2, blah 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 blah, up to xa20, and then you have you have 20 of type B, so it's xb1, xb2, blah 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 blah, xb20. Okay, and we want what is like the sum of all of these 40 random variables, right? 20 from each. So this would be let me continue using a different color just to so if you add them together. That is the total life of the batteries, the combined life of the batteries. Okay, so this would be the combined life of the batteries. Okay, now the important thing here is that that's a sum of Gaussians. Okay, so this is a sum of Gaussians. And there's a property that we prove at some point that the sum of Gaussians is a Gaussian. That's like an important fact. So sum of Gaussians. Oh, by the way, I should say here, like when everything is independent. So I don't think this is kind of said explicitly in any point of the problem. Sum of independent Gaussians. So like the philosophy is that if you have a couple of random, if you have tons of random variables, so you're not told anything, like especially when you're taking the sum or something like that, you should assume that they're independent. but I'll write it explicitly just so you don't have. I'll make sure to write that explicitly on the problems on the exam so that there's no confusion. But yeah, like when you see like the problems on textbooks or things like that, if there's nothing else mentioned, like the independence assumption is kind of like hidden in many of the things that are done. So you do have to keep an eye on that, because once you have the sum of independent Gaussian distributions, that is a Gaussian whose average value is just the sum of the averages. So the mean is just the sum of the averages, and the variance, that's the more important thing, is the sum of the variances. So in this case, you have 20 of the first mean. The first mean was 50, and you have 20 of the second mean, and the second mean was 30. So let me put here 30. And similarly here you have 20. What was the first variance? The first variance, I mean, here you have to be careful. This is like the standard deviation. So the variance is like the square of the standard deviation. So you should just put 15 squared. Then 20 times the other one is 6 squared. So let's see. So what is the first mean? The first mean is the mean is just I mean, when you add, it's easier to add these two numbers together and then multiply by 20. That gives you 80 times 20, that's 1600. Oops. And the variance is, I think I did it during office hours. It was 5,220. So if you add that up, which means that the standard deviation is just the square root of that. There was not like a good I mean, there's not a good square root. You can start taking simplify a little bit the square root, but you won't find like an actual, just like an integer. So you can just leave it that way. And so that means that the sum is being represented. It's represented by the Gaussian. Okay, and we just want that probability to be greater or equal to 1700. So we wanted this the probability that the lifetime is greater or equal to 1700. And so again, I'm not expecting you to find like the actual number, because I'm not going to be giving you this table of Gaussians, but at least like you should just know how to write it down in terms of like the standard Gaussian, which is, so it would be something like this. And so whatever the number is. Is that making sense?
Professor, how come we squared the standard deviation?
You mean the because the thing is like for the Gaussian, when you're adding up Gaussians, what is additive, like the expected value is always additive, right? That's not too surprising. In the case of Gaussians, what was additive was the variance. So
Oh, okay, so the
that's
standard deviation is not additive, it's the variance. Okay.
right. Yeah, it's like, let me see if I can find it actually, because we did it like very quickly one time when we were doing this thing with the moment generating functions. What could this be? It was right before the central limit theorem, I think, that I wrote that. But yeah, I mentioned that quickly. Where is this? Right, but yeah, the important thing, like, what you have to be careful about that with here it is. Oops! Oh my god, I have to always see. The variance is what adds for Gaussians. So, and it just followed. We did like how the way we did it was like when they were independent. That's the thing, of course, when they're independent. Otherwise, like you don't know really too much of what's going on. But when they are independent, then yeah, the cool thing about independence is that the moment generating function of the sum was just a product. And so when you have two Gaussians, like we had computed the moment for each Gaussian, and then you just see from the formula explicitly that the squares because that's what appeared in the exponent that would add up. But yeah, so that's why I had to square first the standard deviations, because the additivity is for the variance, not for the sigmas. So yeah, that is also a subtle point. So it's good to bring it up. So let me write it in words actually. So additivity for the variance, not the sigmas. Let me see if I can fix it. No, the standard deviations. Is that okay? Are there any other questions about this? Okay, so now let me give you like a cute application of the law of large numbers, which is kind of, I mean, it just shows you how you can kind of get away with and use like very counterintuitive things with the right approach to this probability question. So let me just remind you what the law of large numbers said. Again, like x1, x2, up to xn, blah, 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 and it goes forever. That is a sequence of random variables, right? It was an independent, that's again super important, it's an independent sequence of random variables. And the point of the law of large numbers is that you have to think somehow that they are like copies of the same, like there's like an experimental setup that you're just cloning over and over. So the outcomes of each random variable happen with the same probability. Like I don't know, think if I ever gave this name, that's called IID in the probability textbooks, which are IID. That just means independent and identically distributed. So this means independent and identically distributed. Like the identically distributed just means that like the values that the random variables take are with the same probability. So the probabilities functions or densities, however you want to think about them, are literally the same from one random variable to the next. So this just means like they're like kind of like the same probability distribution. And then what like the law of large numbers, that was basically the probability, you know, in the limit when you add up these random variables and you average them, the probability that differs too much from the mean. All of these random variables have the same mean, so that's like here when I write mu, that's not ambiguous, because by hypothesis all of them have the same mean, and the mean for this average sum is also mu. So mu here is like kind of like the common average, common expected value, or this like the expected value which is shared by all of them. Here's your expected value. So, I mean, it said that the probability that this average that you're computing differs from the theoretical average is kind of very small once you take n sufficiently large. Now, in practice, how is that used in practice? Like, so this is like useful to write down. So in practice, how this is used. I mean, you don't you never have like an infinite number of experiments, right? So you have to say that, you know, for n large, whatever that means, like you would say, well, x1 plus x up to xn over n is can be approximated by this expected value. Or if you prefer, you know, usually when I write something like this, I just mean approximated. And so that just means that x1 plus x2 up to xn, it is like, this sum is like n times mu. Okay, so this is like in practice how the, you know, that, like, you know, like the law of large numbers would be used like in either version. It's just saying that when you add up a bunch of random variables, that is roughly like the values that sum takes is roughly like n times the mean. Okay, let me show you an example so that you see like how this actually is used in practice. So here's like something we can start with. So let's start like with the discrete random variable. So here's like an application. This is like a very cute application of this stuff, which is used for data science. So let's start, like, just to make it more concrete, let's start with a discrete random variable. I will call it T, because you'll see I want to reserve the letter X for something else. So like the values that T can take, I'll put them on the real line so that it's easier to visualize. So T will only take, how many did I wrote? You wouldn't believe how much time it took me to create this explicit numbers. I don't know why it took me so much time, like, but it was kind of frustrating. But I just wanted like the numbers to come up very nicely. So like, let's say the T takes either the value 0, 1/2, 1, 3/2, 2, and it's symmetric, so it would be -1/2. It could also take the value -1, -3/2, and -2. Okay, so it's like perfectly, you know, like if it takes a value, it takes also its negative. So let me I need a little bit more space here. -2, -3/2, and then -1. Okay. So those are so T only takes one of how many values do we have here? Like only 9 values. There are only 9 possible values. And let me put below each value the probability that it can take those values with. So I'll put, let me put them with a different color so that they're not confused. So the probability for that it takes a value 0 is like 5/25. I could write that obviously as 1/5, but I just want to write every probability as a fraction with the same denominator. So that's why I'm doing it this way. And then 4/25, 3/25, 2/25, and 1/25, and then like the same goes on the other side. 4/25, 3/25, 2/25, and 1/25. So I mean, like the reason, the way I came up with this, well, so the difference, like, so the thing is like the weak law is a statement for like the probabilities that the random variable differs from the mean. The thing is like it's like a little bit of a notational. The thing is like the random variable is literally like a function, right? So the weak law is a statement about the sorry. The weak law is this statement about the probabilities, right? The thing is like when you look at something like this, right? This is a function. Like I kind of try to emphasize that, but not too much because sometimes it can be confusing. So it has a domain, right? So the strong law of large numbers is a statement about the for each point in the domain, what is this limit of the comparing this limit? You're right. It's more right. It's more like a statement. A point. Okay, so the strong law is like a point-wise statement. It refers to what is happening with for each input of the random variable. The weak law is more like a statement like about the probabilities, if that makes sense. But yeah, it's like a subtle difference and it can be confusing. I only did the weak law, but right, like the point is like since the sum is like a random variable, you could try to like fix an input, a point in the domain of the random variable and see what the limit of that is, and the strong law is about that. But yeah, I mean, it's not it doesn't matter too much if you confuse them in our class, or want to take them as being identical. Like it won't cause too much of a confusion, but it is right. Like one is kind of like a statement about the probabilities, and the other is like a statement about what's happening with every single point. Like the functions, the domain of these random variables is usually called the sample space in some weird terminology. So it's kind of like a statement about the limits of the sums at every single point of the sample space, or not at every single point, but like at points that have probability 1. So it's just like a little bit of very confusing thing to the details of that. It is the strong law is kind of better reserved for like a more advanced course, but it's more like it's more like about what's happening with the points on the domain of the random variable. But yeah, it's just you need to get into more details. Like, but I think the book does it actually. But no. It's not. It is not the same statement. No, definitely it's not the same statement. But yeah, if you come to office hours or at some point, I can explain it to you. But it's just like a little bit it can be very, very mind-boggling to like it can be confusing if I try to explain it here, but yeah, it is. No, that's why it definitely is called the stronger law. Yeah. Kind of like, okay. Let me say like this, like what you can think about it like this, when it says a probability, that refers to an integral, right? Or think of the continuous case, like where the random variables are continuous. This is like a statement about the behavior of certain integrals, right? The strong law is more like a statement almost about the points, how so when you integrate, you're kind of like you're looking at all values at the same time. The strong law is more like a statement about what's happening with every single value in the domain. So like the probability, this probability computation is more like it's an integral thing. Whereas the strong law is more like a statement about what is happening with every single almost like every single value of the density function. I mean, it's not quite that, but it's like closer related to that. So it's kind of like, you know, these, it's the difference between like the behavior of like, the integrals, like the weak law is kind of more like about the behaviors of the integrals, and the strong law is more like the behavior of the actual points in the domain. But yeah, it's not too easy to explain, but because we didn't spend too much time talking about like evaluating the random variables at points, which you can do. So with random variables, we just more or less computed their probabilities. So, but yeah, they do not prove the same statement. Definitely, that's for sure. So let me just go back to this example. So the idea is that right. So the idea is like these are the values on the top. You will see the values that the random variable is taking. At the bottom, you see the probabilities with which each value occurs. So if you see like the way I created this random variable is that it will be symmetric about the origin. The maximum probability happens at the origin, right? So with 20% chance, it takes values at the origin, right? And it kind of starts like the way, I mean, if you look at how the probabilities are decaying, I kind of actually try to decay, make them decay along like, you know, using like a straight line. So if you were to grab these probabilities, actually you get like two straight lines. Like, so the graph of the probabilities, you know, like looks like points on a triangle, basically. The only reason why I tried to do it that way was because I wanted nice numbers. So the first thing that's nice, I mean, at least under my, you know, for my taste, is that like, you know, the probability that t, like the one thing that is nice is that the probability that t, you know, the probability that t equals 0 or plus or minus 1, right? That would give you, sorry, plus or minus 1/2. That is like, that corresponds to, you know, this one, or this one. That is roughly, I mean, that is 13/25. So that's, you know, a little bit more than 50% of the chance, right? So more than 50, a little bit over 50% of the time, it will take values in one of these three numbers. What are these three numbers nice? I don't know if you remember like the discussion that we had at the end of last time when I talked about the weird behavior of spheres in higher dimensions. You know, I don't know if you remember this. But if you remember these spheres, when I talked about this, like these squares that are of length 1, you know, were always, you know, since on each direction it has to have length 1, you know, the maximum value that these sides like could be is like -1/2 or 1/2. Like the corners could be way further, right? But like the you know, the midpoints of the sides, or I don't know how you want to call them, that they are like between -1/2 and 1/2. So it's kind of like saying that, you know, if you thought about it like just like if you just look at these squares and you just focus on one direction on one axis, it's kind of like these points between -1 and 1/2. I mean, all those points like lie between -1/2 and 1/2. So in other words, like only more than 50% of the time, you know, this random variable, like, you know, one of the coordinates would be inside this unit square, and then the probability, like, you know, the probability that it would like that the random variable well, let's put it actually as t equals plus minus 3/2 or plus or minus 2. What is that equal to? That's like 6/25. So only like rough, like, so this like refers to these points. So only like 25% of the time, this random variable would be like kind of outside this unit sphere, right? For sure, with certainty, because like for the unit sphere, you have to have distance 1, or if you want to think about the unit ball, it has to be, your distance has to be 1 or less. So this is like roughly like 0.25%, right? So like only 25% of the time, like this random variable takes a value that would be outside, more than a distance 1 from the origin. Okay, so now what am I going to do now with this random variable? This is like, and it's not too important that I chose this particular random variable. It's just I wanted like a very concrete model for you to think about it. But you like almost anything would have worked that has the following two properties. So like this one should be easy. What do you think is the expected value of this random variable?
Just 0.
It's just 0 because it's symmetric about the origin, right? Like I gave everything the same probability. So that's usually easy to achieve. Like what took me a little bit of time was to play with the number so that, its variance would be 1. But you can check that. So like the standard deviation is also 1 in this case. So it has mean 0 and standard deviation 1. And again, it's not too much, like it's not too important that it's not too important that I chose this particular model. It's just I wanted like some model of a random variable with those two properties. You could also have tried to play with the like discretization of like a Gaussian or other things to do it, but I mean that's not too important. Now imagine that imagine that you're going to work with a vector with n entries. So let's call these vectors with. I'm actually going to work with 2 vectors with n entries. So let's call them y1 and z, y and z. Okay. And what will be like the important assumption here is that each of these individual coordinates, right? Each of these entries, y or zy, yi or zi, the reason why I'm writing them with uppercase is that you should think of them as each of them being as a random variable. Okay, each of these entries, yi, zi, is as a random variable. With the same, which is id to t, which is id with t, or to t, I don't know what would be a better way to say it, meaning that it has the same probabilities as t and it can take the same values as t. So it takes the same values as t with the same probabilities. Takes. Okay. So like just to make this more concrete, what I'm trying to say is that if, for example, if you look at the third entry of the first vector, right, this is a random variable that can take one of 9 values, which 9 values, these same 9 values that you see here And each of these 9 values, the probabilities that it takes those 9 values are exactly this. But the same is true for this one. So for the nth entry of this vector, it takes the same 9 values as t with the same probabilities as t. So it's kind of like making n copies of t. You're making n clones of t and using those as the first as the entries of y, and then you're making n copies of t and using those as the entries of the second vector. Is that making sense? So it's kind of like, it's like you're making 2n duplicates of this random variable t. It's just that the first n, you think of them as the entries of a vector, and the second n, you think of as the entries of another vector. But I mean, if you prefer, you can just think of it as a sequence of, n random variables followed by another sequence of n random variables. It's just that it is useful to, keep them like, separated by entries, because like I will think of this as a vector. And then, so in particular, that means that, the expected value of each coordinate, right, is always 0, and the variance of each individual coordinate is always 0. Okay, sorry, it's always 1 because there was a property for t. Okay, now let's assume that all of these are independent. So here's like the important assumption. So assume y1, y2, blah 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 blah, yn, z1, z2, cn are independent random variables. So what is the, okay, so now we get to the interesting part. What is the length, like, do you remember, okay, so what is the length of a vector squared? What is the formula for the length of a vector squared? That's just the Pythagoras theorem, right? So this is Pythagoras. So it's y1 squared plus y2 squared plus blah plus plus yn squared, right? But if you see, that is adding these it's a sum of random variables, right? So what is the expected value of y squared? Well, it is the sum of these expected values. And can anyone tell me what is this number? We kind of have it written, but not in the way. But it's almost, the answer is more or less there. Well, it's just 1 because, like, since what is the variance of the random variable in general? What is the variance of yi? That's just e of yi squared minus e of yi squared, right? If you remember the variance formula, but the mean of yi is 0, so there's no difference between the variance and e of yi squared. Is that making sense? So that is just this is just, each of these is 1. Is that okay? So I'm just saying the average. So what does this mean? so that means that the average length square of this vector is n. Is that making sense? So the average length square of the vector is n. And then because of the same logic, the average length square of the second vector is also n. Is that okay? It's the same argument. But here's another way to think about these. So here's another way to think about this. Let's call xi. Here's another interpretation. Let's call xi yi squared, for example. So like the formula that I just gave you for the length squared, which was y1 squared plus y2 squared plus yn squared, right? What is that equal to? That's just x1 plus x2 plus xn. So that means that the length squared, right, is just the sum of these n random variables, right? Oh, sorry. I mean, this is before. Sorry, this is before the expected value, right? So, so it is like the kind of like secretly. This is why I cannot use the letter x before, because I wanted to reserve it for this moment. So this is saying that the long length of y squared as a random variable is just the same sum of these n independent random variables. And so this is the same expression that you see in the law of large numbers. Okay. So by the law of large numbers, what this is saying is that, like, you know, once n is large enough, but like meaning that once your vector has a large number of entries, what they're saying is the sum is roughly n times the mean of each of these xi's. So by the law of large numbers, this is approximated by n times the expected value of xi, but the expected value of xi is expected value of yi squared, and so that's just n. So what I'm trying to say is that what this is saying is that you know, once n is large enough, it's not just that the average value of the vectors of the length square is n. It's just that it's not only it's more than that. It's that with high probability, when you choose a vector at random and compute its length squared, it will be n. So it's more like of a statement about that, not just that the average of the length square is n, but also like if you kind of were to compute this length squares for the vectors themselves, you would get n. Okay, so that is where, like, you know, kind of where the law of large numbers would be used to kind of like remove like the expected value. Like the point of the law of large numbers is to stop working with the expected value and work with the random variables themselves, because like the law of large numbers says that you should think of approximating the sum of the random variables by n times the mean. So it's kind of like it's kind of like saying the sum of random variables becomes more and more constant and that constant is n times the mean. That's like that's the important idea of the law of large numbers. So what this is saying is that like the length squared of y is like n with high probability and then and it's kind of like same argument for the length square of z, that would be n with high probability. Okay, and so why is that interesting? Because you know, okay, how is this useful? Because now let's look at something like the length of y minus z squared. Well, the length of y minus z squared, you can compute it as, if you remember the dot product properties, the length of a vector is just the dot product of that vector with itself. So if you use the distributive property, that's y dot y minus 2y dot z plus z dot c. Okay. And this is like, I mean, this is also called, I don't know if you ever did it, it's called the parallelogram law. It's just saying that the length of y minus z squared is the length of y squared plus the length of z squared minus 2 times the dot product between y and z. Okay, but then let's see, this is just give me a second. Okay, yeah. Right, that's what it is. But at the same time, what is that? Another way to write this is, you know, this is like the sum from y equals 1 to n, yi minus di. You can write it in terms of the entries, right? So it could, you could write it like this. I mean, I guess it's going to be the, right. I mean, it's kind of the same, like, just like if you prefer to write it like for each sum. Okay, yeah, right. So, okay, I'll write it. No, I mean, I'm redoing this, like, it doesn't matter. So, things. Yeah, I'll write this like this. That is cool. But now, what is the expected value for this quantity? Well, is the expected value of, remember the expected value is additive. So you can compute the expected values of each term individually. But what was the expected value of the length squared? That was n, the other one is n. And then what can you do here? What is the expected value of a product? Well, if the random variables are independent, that's just the product of the expected values. Okay, but each of these expected values is just 0. So that means that the expected value is just 2n. Okay, but the thing is that the thing is that okay, why is that useful? Because by the law of large numbers, once n is large enough, or n large enough, the point of the law of large numbers is that this statement kind of will be true without the expected value. So this is approximately true with large probability. So if you replace this, so if you replace this, let's just replace this with what we know. So what I'm saying is that this one is approximately equal to 2n, but this piece without the expected value is also approximately equal to n, and this one is approximately equal to 2n. Sorry, I mean, each of these summations has length approximately equal to n. So what that means is that the dot product between y and z is approximately equal to 0, right? Is that making sense? And then when was the dot product? When was the dot product between two vectors equal to 0? What did that say?
The vectors are orthogonal or right angle.
You're right. So yes. So I mean, again, this is not an exact equality because there's an approximation involved. But what it says is that essentially the vectors are almost orthogonal, or so this is almost orthogonal. So what this is saying is that in high dimensions, which is kind of weird, if you choose two vectors at random, as long as they're coordinates are independent random variables, if you choose two vectors at random, and they're almost all the time orthogonal. So if you think of one of these, so any two vectors at random, or almost all vectors that you choose at random under this construction will be orthogonal. Under this construction will be orthogonal. So if you think about one of the vectors kind of like z being like the direction of the North Pole in high dimensions, that means that almost all the other vectors that you choose have to be aligned along the equator. So almost all of the other vectors would have to be kind of like almost like close to the equator. Equator for the product to be almost zero, and that actually would show. I mean, what that translates off in high dimensions is that if you have like a ball or a sphere, almost all the volume or the area is concentrated near the equator. I mean, that can be proved more rigorously, but what that means is that in high dimensions, which is kind of weird if you think. I mean, I don't with this high dimensional spheres, I don't know if there's like a good intuition for how to visualize those things, but almost all the almost all the volume of the high dimensional sphere is kind of like concentrated along the equator. What's weird is like it is all symmetric, so you can rotate the entire picture and that continues to be true. So it's like a little bit almost all the volume is concentrated near the equator. Because almost all the other vectors are orthogonal to the North Pole, so almost all the volume of the sphere or the ball, I mean, concentrated near the equator. So I mean, I don't know if you, of course, this is like a little bit advanced application, but I thought it was kind of like just fun to see. Like that you can draw very weird conclusions, like using like a combination of the law of large numbers and independence. But I guess independence is already assumed for the law of large numbers. But I'm just trying to say that there's like a lot of like weird things that happens. In fact, I mean, there's like this cute book about data science. I may post like a copy at least of this chapter if you want to read it. For those who are interested about how all of these things are used in data science, like for like these search algorithms and things like that. So it kind of goes into more detail about those things. There's like this famous thing for the nearest neighbor search that you have to do like a projection, and it kind of uses like estimates like the ones that I just mentioned. But I thought, okay, it's like a fun application to mention. So this probability stuff is actually very useful. Like, after like you have learned a little bit more advanced concepts. But yeah, so for Monday, I think what we should just do is like take time to go over the problems. I also send you tomorrow some more practice problems for you to work on. And then on Monday, we can just go over whatever problems you want to discuss. So I don't plan on Monday on like me doing any specific problems except the ones that you want to ask me. So like, it will, so that I don't, I feel like I have said everything that I needed to say. So just like bring whatever you're stuck with, getting stuck with. But yeah, I'll send you like a longer list of problems tomorrow for you to work on. I'll post this PDF if you want to read it. It's like very interesting actually. So it's just the second chapter in this book. So, but I think it's like the same next one. So yeah, but I'll see you on Monday if that sounds good.
Thank you, Professor.
Okay, see you.
Professor, I had a quick question on the problems for the second exam.
Uh-huh.
I don't know if you have it pulled up. It was just like the first problem. It was saying, okay, consider random variable. It's in the form like C over 2 to the K. And then,
okay. Right. Like you mean like in the actual exam?
Yeah. It was in the practice as well. But I think in the practice they asked find like the expected value, and
Here I asked for.
It ends up being 2, but I kind of followed like the logic, but just like logically it didn't make sense because the values it's taking is like 1/2, 1/4, 1/8. So it seems odd to have an expected value of 2.
Well, okay, let's see. So, okay, but like in the exam, I thought for the expected value of the square of the variable, right?
Yeah, in this practice problem, it's just normal expected value.
Oh, okay. Let me check it because I don't remember. I mean, I know. Do you remember the number? on the PDF guide, or it can come because you said it was on the this one was on the practice exam. Oh, the extra problems I posted
Yeah.
for the exams. You mean? Okay, I got you now. Let me see, like, if I wrote the solutions. Okay. But okay, those C over 2 to the 2k, right? Those are the probabilities, right? But the values themselves are not those, right? The values themselves are the case. So it's like probability that its value 3 is C over 2 to the 3, right? So
I see.
the values are growing. Values are growing linearly, but the probabilities are decaying exponentially. So right, it's like the usual, contest
Okay,
because
that
one
makes
is
sense.
more.
I think I confused it. I was looking. I thought that the values itself was like 1/2, 1/4, but the
No,
values.
right. Like those are just the probabilities. So yeah, otherwise like we would agree. Right, but each of those probabilities, it is being multiplied by something that's growing. It's just that since it's growing linearly, obviously it won't grow as fast. That's why it still converges. But right. Otherwise, yeah, I agree with you. It would not work. Yeah.
That makes sense. Perfect. All right. Thank you very much. Have a good weekend.
No, sure. No, you too.